Okay, let's just review where we are. So again, today's lecture it's just called Physics and Heat Transfer. Where'd we start? Started with energy. We got to power. We did some units. We determined that energy is in fact power times time. We ran through a little home energy example for electricity, just multiplying kilowatts times hours to get kilowatt hours. I showed you graphically what power, energy, and time look like on a figure. I went through the 3 laws of thermodynamics. It's critical that we realize that heat is sort of in the basement of energy. It's the energy basement. Once you've gone to heat, you kind of can't go back. It's fundamental to that second law. I said kind of because you kind of can too. Like all wind turbines are driven because you've got thermal gradients in the atmosphere. Obviously, the heat engines that we use are purposefully making heat. But and I showed you the thermodynamics video showing that at the end of the universe, it's likely that the whole place is just going to be the same boring temperature. And once it's all the same temperature, you can't do any work. Yeah, like if it wasn't hotter on the sun than it is on the earth, heat would not flow from the sun to the earth. Just, if there was the same temperature, there's no exchange to occur. Went through different types of power, linear mechanical, rotational mechanical. We did some electric. We then did fluid power. And then we did heat power. And that's really where I want to focus my attention to. I have not defined enthalpy, but I will do that before we leave. It's actually pretty simple, even though the word looks kind of weird. We then did a pretty run-of-the-mill home energy economics example. Found the volume of a house. Used this heat capacity equation. We converted density and volume into mass so that we could actually use the heat capacitance of air, which was 1 joule per gram per Kelvin. Came up with 6.12 megajoules of heat in a house that's maintaining 20-degree difference from the outside, and then just turn that to money using published values for the cost of natural gas, because that's where we are right now with cheap natural gas. Okay, now there are 3, this is kind of easy to remember, just like there's 3 physical laws. Well, there's more than that, but the 3 physical laws we covered a second ago. There are also kind of nicely and conveniently 3 heat transfer mechanisms. So the first half of the lecture was physics, and now we're doing heat transfer. Okay, so heat transfer. This gets back to that 3rd law where heat always leaks. The universe is always just trying to reach some equilibrium, again, where everything's the same temperature. There are 3 fundamental modes, and let me just go through them. There's conduction. What's a good example of conduction? Well, my hand is at some temperature. I'm going to put it on the table, and the table feels a little bit cooler than my hand. What's that mean? Well, if I had a thermal imaging camera, which I brought mine with me today, but if I had a thermal imaging camera, shot that down on my hand print after it left the table would then be warmer than when my hand was there. Heat was conducted directly from my hand into the table. And here's another good one. I just got to do this while we're standing here. Trick question. What's hotter, the wall or the blackboard or the green board? The wall. Why is the wall hotter? Yeah. It's really all the same temperature. I mean, if I had a thermal imaging camera, the only things that would be hotter than the surroundings would just be kind of us, the machines. But there's with all the air, like the temperature of this chunk of air right here is it's 70 degrees, and that 70-degree air is touching that board, and so they are in thermal equilibrium. There might be a little difference, but they're the same temperature. Same thing here. This chunk of air is touching that chunk of wall. They're in thermal equilibrium. They're going to reach the same temperature, more or less. Now, I had a conversation with a geophysicist the other day who was telling me that you can go and touch natural stone, and I'll just kind of pretend this is actually a piece of slate or something, a piece of natural stone. And it's going to feel colder than putting my hand on the latex-covered drywall. And he was trying to explain that natural stone is always colder than fake stone, like concrete or whatever. It's not. It's just that heat is going to flow out of that substance more quickly than it does from this one. And somebody said, oh, well, the wall's a little warmer or colder because there's insulation behind it, et cetera, et cetera. But right at the surface, everything's the same temperature. And so
if you're sitting inside in a controlled environment like we are right now, then how does the heat leave it quicker than natural stone or? Good
question. Yeah, it's a good question. So why would that be different? And what we'll do is we'll get into two different things. We'll get into thermal conductivity in a second, and we'll also get into the heat transfer coefficient. Two new concepts. But here's a great way to think about it. Go out to the Clark Fork River on a 32-degree day. How cold is the air? Well, it's freezing. It's 32 degrees Fahrenheit. You look in the water, and there's little chunks of ice in there. It's not frozen over, but how cold's the water? It's 32 degrees. Where would you rather be? In the air or the water? So that water is going to suck heat out of you way quicker than the air is because of that heat transfer. Same thing here. Everything's the same temperature, but you're going to feel that stone sucking heat out of you quicker than you are something like, latex. There you go. Does that make so? Two separate things. Heat and temperature are very different things. Heat transfer and heat conductivity are also two different things, and we'll get into it. But that's where we're going. Okay, so that's conduction. And that's just through direct contact. The next one is convection. I think somewhere in your book there's a neat shot of what's happening. Like earlier today, it smelled really bad in this room. I think either I'm used to it or it's gone. You get a little whiff once in a while. Well, I think it's the building. I think the sewer's backing up. So what we would like to do in that case is convect those offensive odors out of the room. We would actually like to blow them away. But just in windows, a lot of times you'll see the double pane windows, and if it's aluminum or something, you'll see the condensation. What's happening there actually is air moving throughout the room all the time. It's being convected, and typically something that's hot and dense will move somewhere that's cold and not dense. So look at your meteorology patterns, etc. That's what moves air naturally. And then the third one is radiation. And those are the only three modes of heat transfer that I've ever heard of. If you know another one, let me know, but that's it. So how is this happening? What's actually being transferred? I'll just start at the bottom. What's being transferred in radiation? What's sort of moving from one place to another one? Heat is moving, but what do we call the chunk or the vessel or the particle or whatever that's bringing the heat? It's shooting out of the sun. It's light. I'm going to do the particle thing and just call that a photon. Yeah. So that's the light particle for that's just what it's called. The energy per photon is tiny, but there's a lot of them. Some are green, some are red, some are blue, some you can't see, but they've been coming to the Earth, 24/7, 365 for a few billion years now. So that is that's one way that energy can get to Earth. Early on, Earth's history, you had a lot of friction when the Earth was forming, big rocks smashing together, gravity, so we don't quite get the fusion that you see on the sun, but you can also have some mechanical energy. There's also a little bit of radioactive energy. So there's in fact some high energy photons that come off of that. So that's radiation. It does not require matter to convey it. It can just fly right through empty space. Okay, the next one is convection, and again, that's wind, heat, just heat transfer from thermal gradients. What's moving there? Could be air.
Gas.
What's air made of? Yeah, gas. It's just molecules.
Nitrogen.
Yeah, molecules of nitrogen, air, what have you. And the way to think about that is, and heat itself is really no more than kind of the, what's that?
It's still all zeros, bro.
Oh, it shows up in the icon as zeros, but we're rolling, yeah. I know, that was some good stuff we would have missed, right? So heat itself and temperature can really be thought of as just the average velocity of the molecules in a system. So the faster they're moving, the faster they're vibrating, the hotter something is. Like fundamentally, that's all thermal energy is. It's just vibration at the atomic scale. So all you're doing in convection is just moving one set of quickly vibrating hot molecules over somewhere where there's a bunch of slow moving molecules somewhere else. That's convection. And then conduction, on the one hand, it seems pretty simple. It's the one I started with. You just touch your hand on the table and then the heat goes there. But like my hand didn't go into the table. I wasn't like firing radiation beam. Well, I was a little bit, but in general, firing radiation beams out of my hand into the table. But heat transfer did occur, and in this case, it's actually it's kind of weird, but they're actually called phonons.
Phonons?
Yeah. You don't hear that typically in the building trades, but that's all it is. My hand, all the molecules, atoms, whatever, they're hot because they're vibrating. And all I did when I touched the table, the vibration of the molecules and atoms in my hand slowed down, and the vibration of the ones in the table sped up. And so each one of those vibrations you can almost just think of as I don't know, a bunch of little miniature guitars or instruments or what have you. And then when they slow down, they're just like a lower vibration. And so in that sense, just how radiation can be thought of as just little packets, little photons coming one at a time. And obviously molecules, nitrogen, oxygen, what have you, and it's just kind of one at a time, moving quickly. Same thing with the phonon. I want to look that up really quick. It's kind of fun to think about.
Conduction through direct contact.
Sorry, what?
Conduction through direct contact.
Conduction through direct contact, absolutely. And you're just slowing down the average vibration in one chunk of matter and picking up higher vibrations in another. What were you saying?
It's just an electron with the energy level filled. The energy levels in the molecule, there are more electrons in the molecules than there are energy levels, like a string
Yeah.
that vibrates, in
Yeah.
the middle.
Mhm.
It doesn't vibrate on both ends, and you can't use that. So the ones that we can't use for like electrical conductivity
Yeah.
conduct heat, so it's just
Yeah,
basic.
I don't think it's necessarily like the electrons are definitely coming along for the ride, but I think what they're showing here is just individual atoms or molecules, doesn't matter, one or the other, same difference, sort of bouncing back and forth. And so one's, vibrating, again, just back to the hand example, they were vibrating quickly, slow it down, they vibrate more slowly when it gets colder. If you get it going fast enough, yeah, you can feel the heat, and that's kind of what ultrasonic therapy is and all that. So it's just kind of going from a microscopic mechanical phenomenon to a larger scale temperature phenomena that we can actually feel, with our own little heat sensors. Okay, so those are the three fundamental units. let's throw a couple equations at them, because I already mentioned the fact that even though the chalkboard and the wall are the same temperature, they feel different because of a couple different things. So let's look at this. Okay, thermal conductivity. Let's just check out.
Based upon what material everything is made up of.
Yeah.
That then dictates how much of the heat goes into which type of material to keep the room at its 70-degree temperature.
Yeah, it's a good way to think of it. Yep. Mm-hmm. Just think right back to that air-water example. A lot of times too, in Missoula, it can get pretty cold. It doesn't feel that cold because the humidity is low. So you can think of those water molecules in the air at a higher humidity sucking heat out of you quicker if they weren't there.
Yeah.
Okay. So let's just take a look at thermal conductivity, and I'll just and I know there's some problems like this in the Dorsey and Krieger book. Okay. We already know what watts are, and this is going to, I mean, right here is going to be your bread and butter for thermal efficiency in your house. We know what watts are, that's power. We know what meters are, that's length, and we know what K is, that's Kelvin. You can also just think of that as Fahrenheit, it doesn't really matter. So what this is telling me is that diamond will conduct heat very quickly. It'll either give it or take it. Steel is less, mercury is less, there's ice, there's glass, there's concrete. Let's see if we can't do a little thermal conductivity example. Scholarly articles. Yeah, conductive heat transfer. I like this engineering toolbox too. Okay. All right, here we go. So remember before I was talking about I used that little cube for heat transfer. That's where that was coming from. I already mentioned, when we just mentioned and just looked up the thermal conductivity of the material, and again, just like we just saw, that's measured in watts per meter per Kelvin. So let's just see if we can't do one little example. And there is nothing wrong with just doing this one sitting right here in the engineering toolbox. So, yeah, this is perfect. So, a plain wall is constructed of solid iron. We could go back and replace that with solid wood, solid insulation, or a combination thereof. Thermal conductivity is 70 watts per meter per Celsius. The thickness is 50 millimeters, and the length and width is 1 meter by 1 meter. Okay. Now let's just take one more peek at the equation before we solve it, and I'm just gonna copy it right here into my notebook. This is also going to get us back into the into what the R value is. The R value, as it turns out, is just a combination of all three of these modes. You're never going to go into the hardware store, hey, I want a K value of this and an H value of this and how many photons. The R value takes care of all three of them. Just so you know. At the end of the day, it's all going to boil down to the R value.
Interesting conversation if you did.
Maybe we wouldn't have a conversation.
Oh, what? Who knows, though? You might have some physics majors from our own school working out at Home Depot. You never know. You always hear about the philosophy. Well, I guess you hear about the philosophy major waiting tables, but maybe not the physics guy. Go to Lowe's.
But if he's a philosophy major and he's waiting tables, he's probably not very good at philosophy.
Be waiting tables.
Philosophy is actually hard science.
I know. I don't mean to. Rip on the poor philosophers. I'm just trying to see if Christopher Preston is listening or not, if he gives me heck for saying this. Okay. You don't have to commit this thing to memory. This isn't something you're going to have to know, but if you wanted to try, you could I kind of look at that and say, like, it's Q cats, maybe, Q and then the word cats with that funny delta thing thrown in there. What are each one of these things? Well, this thing is the one you care about. It's also, I wrote this before, this is actually power thermal. This is thermal power. It's how much thermal power is leaking out of your house. We talked about heating degree days. We talked about that 5 or 6 cents worth of heat in your house. This is happening all the time. Like right now, Q is happening, but it's flowing out of this building and out into the outside. If it were a summer day and we were trying to keep it cold in here, Q would be pointing the other direction. At some point, it doesn't go either direction because there's no delta T. It's the delta T that drives it. What else drives this thing? Well, the bigger the wall, that's how much area, the more heat transfer you're going to get. The thicker the wall, I think that's right, yeah, material thickness, the less, because it's just going to take longer for that heat to get through there. And then the material, too, is going to count. So this think of S, well, that's the thickness. That's like a geometry issue. A is the area. Again, that's a geometry issue. The delta T, that's temp. You can think of that as a physics parameter. And then K, that's the thermal conductivity. Yep. The thermcon. And that's a material constant. Yeah. And and getting back to where we were before, this delta T in some ways is kind of your across variable, and then these guys are your the rest of these are your through variables, because the heat is passing through an area, through a thickness with some temperature. That's why I kind of hesitated to write it all out exactly right. This is just one example of a thermal power equation. So this takes us right back to that first page or two, thermal power. Okay, let's just bang through this one little problem. So in this case, and I'll just reiterate, and if you want to follow along, it's always good to put the pencil to paper. So we can go back. Solid iron, let's just double check. I think we had a, yeah, let's just go back and look at that other page. I always like to double check. Wikipedia, let's see if we can find iron. Sometimes there's a table. List of thermal conductivities. Iron, where are you? Yeah, so I'm looking at 71, 72, 55, and these are all experimental values. Somebody went out and measured the thing, took the time to do the physics. Let's just make sure our units are correct. Watts per meter per Kelvin. And let's get back to this other.
Book has everything but iron in it.
Oh, really? Yeah, I'm like, well.
Oh, steel, there's 310 for steel.
Okay.
But it's a little bit different than iron.
Yeah. So watts per meter per Kelvin, same thing, watts per meter per Celsius. There's one change. So there. So let's go ahead and just pop that in. So I'll write it like so. 70 watts. I'll put meters down here. I'll put degrees C down here as well. That's our K. Our area, that's just how big the wall is. And window over there is about 1 meter by 1 meter, so we can very easily visualize that. So 1 meter times 1 meter. The change in temperature. Now in this example, this is probably more like, gosh, I mean they're actually above boiling. I mean this would be an application where you probably actually have a boiler. You know, water is boiling inside of this thing. It's above it's above boiling temperature. Anyway, so 150 minus 80. I'm just going to go ahead and write that in as 70 degrees C. And then they gave the wall thickness as 50 millimeters. Well, I know that is a 20th. I'll just divide, 50 by 1,000, and that comes out to be 0.05. So I'll put that down here. Divide the whole thing by 0.05 meters. Now all I have to do, and remember, you're always solving 3 problems at once. In this case, I don't see any powers of 10, so it's a little bit easier. But I'm going to cancel my degree C, cancel my degree C. I'm going to cancel this meter with this one. It's in the denominator of the numerator, so those 2 guys cancel. And then this meter in the numerator is going to cancel with this meter in the denominator. I don't have any other powers of 10 to deal or worry about. Pull up my calculator. Pull up my calculator. Double check what number I'm dealing with. So I've got 70 times 70 divided by 0.05 equals. So that's actually a lot of power. We're looking at 98 kilowatts. And, well, if you were in fact running a power system where you need a lot of heat, that'd be pretty reasonable. So equals 98 kilowatts. In a house, you're probably not going to have solid steel walls. So let's just do another little example.
So we figured out we're not supposed to use that for construction.
Yeah, there you go. Check that box. Not solid iron walls.
Maybe sturdy, but efficiency.
Yeah. So let's just go down. What's kind of neat, what you'll find is that air itself is a barrier. If you look at some of these houses around town, you'll see these guys sort of putting like what looks like fencing on their house. They're just forming a little air pocket or an air barrier. Like, what's that going to do? Well, it keeps that. It's like a blanket in some ways. It just kind of keeps that conductive loss. I don't know exactly, what the cost benefit is there, but on the other hand, if you got a bunch of wood laying around, and you got some time on your hands, and neighbors don't mind how it looks, slap it up there and see if it saves you some energy. So, but let's just go down. Here's concrete. I'm just going to call concrete a value of 1. So it's 70 times less thermally conductive than steel.
What are the units on that?
The units are watts per meter per Kelvin. So let's do one more little example, and I'll take a break. One more example, and I'll take a break. So let's just do concrete. Oops, TE, and let's make this wall. Let's just make it a foot thick, and we'll just stick to SI units. So we'll just say S equals 1 foot equals 30. Equals 300 millimeters. Equals 0.3 meters. We know that K, we just said, equals 1 watt per meter per Kelvin. let's just stick with our regular delta T for a room. Delta T is 20. Well, 20 Fahrenheit equals, what do we say, 11 Kelvin? And what else are we missing here? Oh, let's just do the area. Let's just go ahead and do the area of that house we looked at before. What do you say? Let's just.
15,000.
Yes. So we got to go back to our house, and 2,000 square feet. What's the? Let's just do the square root of 2,000 really quick if we can. Hello, 2,000 square root.
40 million.
Let's call it 45. So let's just say the house is, let's just say it's 45 by 45 by 8. So the area of the house equals 2 times 45 times 45, right? That's the roof and the floor. And then, so A1, A2 equals 8 times 45 times 4. So that's the area of all the walls. So let's go back to our calculator. 45 times, and I'm going to just use 3 sig digs here, times 2 equals, that's 4,000. Does that sound right? Yeah, if it's a 2,000 square foot house, single level, top and bottom, okay. Yeah, that's right on. So 4,000, we'll call that the top and bottom, and let's do 8 times 45 times 4 to get all the walls, 1,440. So 4,000 plus 1,440, we're looking at 5,440. Did I do that right? A equals 5,440 meters squared. That's the area of the house. Man, I got a 50. Is that, oh, you know what, I'm sorry, that's in feet, That seemed too big, That's feet, that's feet squared. Right, yeah. That's in square feet. Tools, eraser, medium. Then we'll convert that to feet squared, pen, so feet squared, there we go. That's the total surface area of the house. We didn't assume it had an attic and all that. We're just kind of like figuring out, how quickly is heat flowing out of this house if it's made of just pure concrete, and hopefully the number comes out about right. So let's convert square feet to square meters. 5,440 feet square to meters to square. You guys probably have this app on your phone already, don't you? Okay. 500, I'll call it, that sounds about right. 1/10, there's about 9, yeah, square meters. I'm just going to call it 500 square meters. Equals 500 meters squared. Now, where were we? A equals 500 meters squared. We did it once with the online example for steel, and that's kind of a funny looking cue. If you want to make your cues look a little bit better, you can put a little tail on it like that. I just remember that trick. So that's for the iron house. Now we're going to do it for the concrete house, where the heat transfer coefficient K is much lower at 1 watt. So here we go. So Q equals 1 watt per meter Kelvin. Make sure I get everything in the same order here. Now I need my area. My area is 500 meters squared for my 2,000 square foot block house, 500 meters squared. My change in temperature, I converted my 20 Fahrenheit into 11.
266 Kelvin.
Oh, yeah, the absolute temperature is 266 Kelvin. All we care about is the difference in temperatures.
Oh.
If we were in a spacecraft, outer space at 3 Kelvin, we'd use much larger numbers, but here, right on Earth, we're just looking at the delta T, which is just 11 Kelvin. And then finally, what did I say? My wall thickness is 1/3 of a meter, so 0.3 meters equals. Double check my math here. So 500 times 11 divided by 0.3 equals.
18.3 kilowatts.
Yeah, 18 kW. Now, did I not say, like, very early in the lecture that typically we spend more, well, we consume more energy thermally than we do electrically? That's just one example. I mean, if you had much better insulation, obviously that number is going to go down. But in general, your thermal consumption is going to be 5 to 10 times higher than your electrical consumption. That's kind of the bad news. The good news is that in general, the same amount of energy sent to your house in natural gas costs less than the same amount of energy that it does to send it in the form of electrons. And there's a lot of reasons for that, and don't want to get into all of them. But anyway, there's a, so you asked before, so you've got this many megajoules of energy in your house, or this many therms or BTUs. Well, that's an estimate of how quickly it's leaving. So, okay, let's take a little break there. I think we've probably, gone a little over 30, but that's okay. That's, again, this is kind of your bread and butter of heat transfer in the house. The other two things I want to cover, and I'll get back to them, are enthalpy, so you know what that is, and then I'll look at the heat transfer coefficient, and that's about all we'll have time for today. Oh, a little bit of R value too, those three things.